Hi, good morning. I'm Dr. Jyoti. I'm going to present development of compact indigenous TeraHa systems for medical diagnostics and NDT applications. This paper has been presented by TeraLumen Solutions, my colleague Dr. Somik, Sonia Leni, Dr. Syam, and Dr. Bala. If we'll see the terahertz radiation, it mainly lies between microwave and infrared, that is zero point 0.1 to 10 terahertz, and the energy level is very low, that is 4.1 milli-electron volt. There are few advantages or few properties of terahertz radiation for which it has been used for so many applications. The main advantage is transparent to dielectrics like wood, package, and package materials, so it can be used for package inspection. Since because the energy level is very low, it is the radiation is non-ionizing, so it's safe for human body, can be used for biomedical applications. Due to the sub-millimeter wavelength, it can be used for multi-layer coating thickness measurement. If we'll see the terahertz imaging applications, it can be used for various applications such as package inspection, food quality monitoring, for pharmaceutical industry, aircraft component inspection, oil and gas industry, automobile industry for multi-layer coating thickness measurement, and biomedical applications. The factors influencing the adoption of terahertz technology is mainly as you keep on increasing the bandwidth, the cost is increasing significantly higher. So that is the limitations of terahertz technology right now. The few applications of terahertz technology, if we'll go for, it's mainly the medical diagnostics. Due to the inherent advantage of terahertz for water, like water will strongly absorb terahertz radiation. It can be used to differentiate benign and malignant tissue. So it can be used for accurate cancer margin detection. You can see the refractive index and absorption coefficient. Terahertz is having very higher refractive index of tumor tissue than normal tissue. So we'll get better contrast between the benign and malignant tissue. Also, we can see as you said, is transparent to dielectric materials. So it can be used to detect internal defects of fiber composites GFRP samples. This paper has been presented by Hari at SPI 2019, at which they have used adaptive sampling to detect 0.5 millimeter defects in GFRP samples. So it can also be used by thermal barrier coating samples. This paper has been presented by joint collaborations of TeraLumen Solutions and IIT Madras and CSR series, at which we have compared the terahertz measurements with IR measurements, and we can able to detect the coating thickness measurement of more than 20 micron. So these are the few applications where terahertz can be used. Also in pharmaceutical applications, we can use for multi-layer coating thickness measurement, on the chemical properties, on imaging of detection of illicit drugs. So we at TeraLumen have developed a continuous wave compact terahertz system in which the schematic of the system goes like that. Goes like this. We have two distributed feedback lasers, DFB laser 1 and laser 2. The optical signal has been combined by a splitter combiner. So one beam goes to the emitter and the other optical beam goes to the terahertz detector. We'll give a bias will give bias to the emitter, which will to create the terahertz radiation, and the detector will be used to detect the terahertz radiation reflected back from the sample, and it can be used to the it can be given to the lock-in amplifier. So the lock-in amplifier will be used to measure the low noise signal, or the signal from signal to noise ratio. So the product specification goes from 0.1 to 1 terahertz with 50 to 60 dB SNR. The geometry will mainly use for biomedical applications and NDT applications. It's in reflection mode. It's a compact device. So if we'll see the development of terahertz systems at CSR, we have used the systems during my PhD, which is very bulky and very expensive. It has been procured from Menlo and Toptica. So we try to make it compact and low cost. These are fast packaged terahertz systems where we have complete electronics and optics. We try to make it in a compact device. And the recent version, which is very compact, you can see the terahertz probe, and the complete electronics and optics goes like a small device or a compact terahertz system. So the key feature, as I said, is a compact and cost-effective. We have developed our own GUI, graphical user interfaces, and advanced data processing technique for millimeter level coating thickness measurement. We have done artificial intelligence enabled customized turnkey system, and target applications are mainly terahertz for NDT and terahertz for biomedical applications. That is for cancer margin detection. So continuous of terahertz systems for biomedical applications. As we know, India cancer starts. Breast cancer is the most common cancer among women, and oral cancer is the most common cancer among men in India. 30% of cancer surgeries fail due to inaccurate margin detection. That is 30,000 repeat surgeries per year. So when doctors wanted to remove the cancerous tissue, they will remove some extra amount of healthy tissue that is called negative margin, which is desirable. So in some cases, since because we do not have any intraoperative device available, although they will remove the cancerous tissue, still some amount of healthy tissue will be left out in the body. That's called positive margin. So the current process is time consuming and cumbersome. We need an expert pathologist for the assessment. So advantages of TeraLumen technology, as I said, it will give you much quicker decision, 5x to 6x faster decision compared to the existing technology. The surgeons will and patients will spend less time in the surgical environment. The decision is based on entire sample instead of a subset of sample, and the accuracy is with millimeter precision. So the technology, we have combined terahertz and artificial intelligence algorithm into it. We have done the measurements of few formalin fixed samples and few fresh samples. You can see the fresh tissue will having higher absorption or the and higher reflected intensity than the normal tissue. So cancerous fresh tissue will having higher reflected intensity. Based on the intensity map, we can delineate the cancerous tissue than the normal tissue, and it has been compared with the HNE slides, which has been marked by an expert pathologist. I can show you few more results where we have compared our terahertz results by the HNE slides, and the terahertz radiation or the terahertz technology can differentiate the benign and malignant tissue at par of the histopathology slides. So we have done the classification by using random forest analysis and support vector machine. The feature extraction has been done by principal component analysis. You can see that we could delineate the cancerous tissue and the non-cancer tissue or the benign tissue. So the confusion matrix, which is you can see the true positive is 32 out of 50 samples and false positive is 40. We are getting 90% accuracy, 90 to 95% sensitivity, and 85 to 90% specificity. So the terahertz radiation can be used to delineate the benign and malignant tissue at par of the histopathology slides. So the continuous of terahertz system, we have also done the applications on non-destructive testing, at which we have used the imaging of fiber composites GFRP samples. GFRP samples are due to its lightweight structure. It is mainly used at turbine blades, pressure tank, and GFRP also used in aircrafts due to its lightweight and waterproof properties. So the motivation, mainly the non-destructive applications motivation, is mainly due to the, you can see the aviation industry spends so 82 million of money for maintenance and repair. So the NDT or non-destructive testing is important for any industries. Challenges of conventional technique or at NDT technique industry lack suitable measurement testing techniques. That's mainly ultrasonic technique, need complex coupling medium. Radiography techniques are very bulky and very expensive. So these are mainly cannot be used for fiber composites and dielectrics and sandwich structures. So terahertz is a novel technique most suitable for non-metallic materials such as FRP composites and foam samples. The key challenges of GRP are mainly the impact damage. So few composite materials will get damaged due to low speed, maybe bar strikes, hail shocks, and impact on maintenance tools. Internal defects will be there while processing itself, and the water ingression properties due to environmental moisturized conditions. So we at TeraLumen have imaged few GFRP samples. This is one impact damage has been created purposefully, and that has been detected clearly due to the low terahertz radiation at the defects due to scattering. We can say that the terahertz image clearly shows the damage or the internal or the defect has been from the GFRP sample. We have also tracked the water ingression property. You have this area has been water immersed, which cannot be seen by the visible or naked eye. It has been clearly shown from the terahertz images. So also we have created two internal defects. Here this defect is around 6 mm defect, and one more 1 mm defect. The 6 mm defect has been seen from the terahertz image. Also due to the wavelength resolution, the 1 mm defect is not visible in the terahertz beams due to the larger terahertz beam spot. The future applications of terahertz technology, it can be used for multi-layer tube wall measurement. Even this is one terahertz view paper. So they have at which the terahertz device has been used by a robot. It can be used for online monitoring of coating thickness measurement. This also another paper has been Toptica, published by Toptica, in which they have shown the air packets, that is for terahertz for inline monitoring. So the future applications goes like this. We can see the air inclusions, less than very small air inclusions can also be visible, and multi-layer coating thickness up to 5 micron has been measured. Below 20 micron also the system can be capable to determine coating thickness. Highlights of the company: the company has been received BILAC BIG grants from Nidhi Prayas grant and few grants from government of Tamil Nadu. And also we have won few competitions like Wharton Startup Challenge, India Sweden Healthcare Challenge, and we have been covered by NewsX, Your Story, and we have finalist at Qualcomm Women Entrepreneur Network. This is the team. This is Sonia, Somik, Lenin, and myself. This is Dr. Bala, Dr. Syam, due to which we could able to achieve this much. Thank you.